Thanks. Okay, so this talk is going to be much simpler than some of the other talks we've been having this week. And so yeah, feel free to stop me and ask stupid questions because we have a sufficient amount of time. So let me just start with some notation which will hold throughout the talk. So X is a Kähler manifold, and G is a compact Lie group. And GC is the complexification of G. So, for example, if G is S1, GC is C star, etc. And G has a Hamiltonian action on X. And this Hamiltonian action has a moment map. G dual, I'll just identify this with G and fix the identification. Okay, and another assumption which holds all the time is G acts freely on the zero level set. So this can be relaxed to G acts with finite stabilizers. But to keep things simple, we'll just do the free case. And before, so what I'm going to talk about is essentially a Hitchin-Kobayashi correspondence, which we have seen a lot of the last week. So I'll just recall some things. So first is the Kempfness theorem, which is the finite dimensional prototype of the Hitchin-Kobayashi correspondence. And what the Kempfness theorem states is that if, in addition to having all these structures, if X also had an algebraic structure, which means that X is a polarized projective variety with GC acting holomorphically, then the GIT quotient, which is in our case, because of this free action assumption, the GIT quotient is actually just the semi-stable locus of X modded out by GC. So GC has a free action on the semi-stable locus because G has a free action on the zero level set, and the semi-stable locus will be a Zariski open set in X. And the Kempfness theorem says that this GIT quotient is same as the symplectic quotient. Okay, and so I'll say what briefly Hitchin-Kobayashi correspondence is. Hitchin-Kobayashi correspondence for vortices. So in order to say this, Hitchin-Kobayashi correspondence is an infinite dimensional version of this. So I need to tell you what the space X is, what the group G is, in order to state it. So the role of X is going to be played by gauged holomorphic maps. So gauged, so this is a definition of gauged holomorphic map. So gauge holomorphic map from sigma to X is a pair AU. So again, this is something we've seen a lot of last week and also this week. Where A is a connection on a principal bundle principal G bundle, and U is a holomorphic section. So this associated bundle, this is just a vibration over sigma whose fibers are X. So so U is a section here, and it is holomorphic with respect to the connection A. So the connection A induces a complex structure in this case on this associated product, because we have something on the base and something on the fiber, and the connection tells you how to put it all together in the total space, and U is a holomorphic section. So that's a gauge holomorphic map, and that is precisely, it's just, you can also think of it as, if you're an algebraic geometer, it would just be a map of stacks. So it's a gauge map to the stack X mod GC. So, yeah. Yes, I'm yet to do that. That's the next thing I'm going to write. So H sigma X is this set. At this point, it's just a set. And in our talk, for most of the time, it's just going to be a set because we just give bijections, except in one case. So it's, I write space, but let's just to obfuscate space of gauge holomorphic maps. And this has an action of the complexified gauge group. So group of complexified gauge transformations. Again, this is a bit confusing. This is not just one group, because in different pieces, the P is going to be different. And this guy really depends on the P. So it's a different group acting on different pieces. So that's the space of gauge holomorphic maps. And we want to say that, so what a Hitchin-Kobayashi correspondence is. So HK for short. So HK is a statement of the form that the semi-stable, the set of semi-stable gauge holomorphic maps modded out by the complexified gauge group is bijective to the space of vortices modded out by the unitary gauge group. So sorry, before I said this sentence, I should actually have said, yeah, this should have gone before this. which is that the action of the unitary gauge group or the group of unitary gauge transformations. So this is Hamiltonian with moment map. And this is precisely the vortex functional. The vortex function, okay, so this is the moment map, and the set of vortices is exactly the zero level set of the moment map modded out by the group of unitary gauge transformations, and this is the semi-stable locus modded out by the complex gauge transformations. So this is what Hitchin-Kobayashi correspondence looks like. And in the vortex setting, in the symplectic vortex setting, I mean, all these Oscar Garcia-Prada and Bradlow's or correspondences, they are all Hitchin-Kobayashi correspondence, where X is just a vector space. But the first kind of non-linear setting was studied by Ignacy Mundet. So he defined the notion of stability when sigma is compact. And proved Hitchin-Kobayashi correspondence. Okay, and the goal of this talk is going to be, our goal today is to look at the case where sigma is non-compact, and not the most general setting, but certain non-compact manifolds, non-compact Riemann surfaces. So in particular, give a Hitchin-Kobayashi correspondence in case where sigma is C with the Euclidean metric. And or sigma is a punctured Riemann surface, and the metric is cylindrical in the punctured neighborhoods. So, so we'll take out a few points with cylindrical metric on punctured neighborhoods. Okay, so that's the goal. So so these first category of vortices, they're called affine vortices. Vortices whose domain is the complex plane. So let me talk about them. Yeah. Yes, thank you. Yeah. It's proper. So therefore, the quotients are compact. So the only source of non-compactness is the sigma being non-compact, but X itself can be non-compact. But there is a convexity assumption, which I'm not writing down, which basically makes sure that you don't escape out to the infinite ends of X. So vector spaces, for example, have that property. Or Stein manifolds, yeah.
Along the same lines, are there assumptions on G? Like, do you need G to have a character?
Sorry?
So X mod G may or may not have natural resolutions.
Currently, if you assume GX freely, it's just a smooth manifold. The stable quotient, if that's what you have in mind.
But if this is a linear action on a vector space, it will never act freely on the 0 point,
oh no, it'll act freely on the semi-stable locus.
Right. I guess I'm asking, are there any assumptions that is there anything needed to be able to define the semi-stable locus? I'm not sure.
No, not really. So if you have, no. If all you need is a polarization, which is the same as choosing a moment map. And once you do that, this machinery of Mumford just gives you a semi-stable.
Could it be empty?
So you want to see the definition of semi-stable?
No, I'll ask at lunch.
Okay.
Thanks.
Okay. Okay. So so here I'm going to kind of alter my definition of this guy a little bit and not consider all gauged holomorphic maps, but instead consider this set of gauged holomorphic maps from C to X that extend gauged holomorphic map from C to X that extends to let me just say it extends over infinity. So I just restrict attention to the ones that extend over infinity. For some G bundle, extends to P over P1 for some G bundle. So these are the extendable gauged holomorphic maps, and the theorem is that, so this is a theorem of myself with Chris Woodward, which says that the semi-stable ones are those gauged maps which map to the semi-stable locus in X at infinity. U infinity lies in semi-stable of X. So that is the semi-stability, which looks much simpler than Mundet's one, if you were to look at that. Yes, thank you. Okay, and with this notion of semi-stability, we prove a bijection. Is bijective to affine vortices. So this is the theorem. And there's actually It can be anything. Sorry? It can be what? I guess it will, right? Like if I'm dropping, yeah, it will depend on yeah. Yeah. Or I mean, you can also just think of these as gauge holomorphic maps on P1. I can also just write that. Maybe just this is. Sorry? No, X doesn't have to be compact. The moment map has to be proper. Yeah. So the quotient is compact. So yeah, so it reproves some of the theorems from last week. For example, Martin Spate proved a theorem of Jaffe-Taubes for us, which is essentially a classification of affine vortices whose target space is X equals C. The group is S1 and GC is C star. And in that case, you see that the semi-stable gauged maps are exactly so the semi-stability just forces that there is no zero at infinity. And this generalizes to compact toric varieties. So you take X to be Cn and G to be a torus, and you get a classification for vortices in the toric case. And another example from last week, again from Martin's talk, is he looked at the case when X is P1 and G is S1. So in this case, the semi-stable locus is P1 minus the 0 and infinity. So then so P1 minus 0 and infinity is the semi-stable locus, and then the semi-stable guys are just going to be meromorphic section. So yeah. Meromorphic sections of and at infinity you can map neither to, so at infinity you can have neither a pole or a zero. So that is the classification of all these of the lumps. And of course, we can also replace X by a toric variety and G by the torus acting on it and get something similar. Okay, sorry. Okay. Do not cross. Should I just start? I'll just start here. Okay, and why did we work on affine vortices? Because they show up in the definition of the quantum Kirwan map. So if you remember, this picture from Chris Woodward's talk, affine vortices are used to define the quantum Kirwan map. So the idea there was if you have a sequence of, so mu is integer mu, and mu is going to infinity. So mu u mu is rho mu vortex on sigma, which is a compact Riemann surface. And what I mean by rho mu vortex is that the vortex, or the ordinary vortex equation, is replaced by scaling of the moment map, or you can think of it as you are blowing up the volume form. And then, so we can show that a sequence of these, if their homology is fixed. So assume that in a fixed homology class, rather equivariant homology class. So once you fix this homology class, a subsequence converges to go to the next board. So what the subsequence converges to is you have a holomorphic map on the quotient. And not gauge holomorphic, just holomorphic. And the reason you end up in the quotient is because the quotient is the zero level set of the moment map. So because you are pushing this parameter up, you're forcing the moment map to be zero. But what happens is that the limit doesn't look as nice because there is bubbling, and those bubbles are so of this form. Just drew this in different colors, which was a great idea. Exactly. And there can be more bubbles, sphere bubbles in X. So these lie in the fiber and are holomorphic, but these guys with the funny shape, these are affine vortices. So the quantum, so these affine vortices kind of detect how much these gauge holomorphic maps differ from holomorphic maps in the quotient. So count of affine vortices defines the quantum Kirwan morphism. So that's why they were interesting to us. Okay. Okay, so that's the end of my second section on affine vortices. But I said that we talk about Hitchin Kobayashi in two different settings. So let me talk about the motivation of the other setting, which is the Riemann surface with punctures and cylindrical metric on the puncture. So that is, and the motivation for those objects correspond to quasi-maps. So let me talk about quasi-maps a little bit. So Jong-Sok spent a lot of time carefully defining quasi-maps, but I will kind of extract the part of the definition which is going to be relevant to us. And I'll say that a genus G quasi-map with K markings is a gauged map, which means a gauged holomorphic map. It's a gauged map sorry, 1 second. The domain has markings on it, P1 through Pk, and it is mapped to this stack with isolated base points. So what are base points? So base points are just the inverse images of the unstable locus. So again, using notation from Jong-Sok here. So unstable is just everything that is not semi-stable. And these would be reasonable cases, complex codimension 1. So the base points are isolated and disjoint from markings and nodes. And the stability condition here is that so U is stable, a stable quasi-map. If so, this is something like what you see in Romão theory, but slightly different, which is that if any irreducible component of the curve, has at least 2 special points, so which is markings / nodes. So both markings and nodes are taken to be special points, and any irreducible component has at least 2 of them. And equality implies that U is not constant on that component. So yeah, so in contrast with in Romão theory, if U is non-constant, you have no conditions about how many markings are there, but here you still require it to have at least 2 markings. So that's the difference. And in this is actually a 0+ quasi-map. This is the 0 stability parameter in Jong-Sok's talk. So this is the only stability condition I'm going to be talking about. Okay, and how is this related to vortices? So the vortex analog of quasi-maps. So the only thing we really need to ensure in these gauge holomorphic maps is that this is the key condition, that base points don't coincide with markings and nodes, and which means that markings and nodes map to the stable locus, and which kind of gives us the hint from here. So here we said infinity should map to the stable locus. And so infinity was a puncture in some sense. So that gives us the idea that we should just put punctures at the special points. So on C, on the domain of the quasi-map, replace nodes and markings with punctures. Whose neighborhoods have a cylindrical metric. And okay. Yeah. Mm-hmm. Oh, yeah, yeah. So I need to impose the condition that there's a matching condition at the node. The evaluation is the same on X mod 1 GC. So yeah, so node is replaced by cylinders and Z plus, Z minus. Means your domain is a long tube. No, this is just a picture. The important thing is that some neighborhood here is isometric to a cylinder. Yeah, that's, you can draw it thick. Okay. Mm-hmm. I see what you mean. Yeah, this is infinite. So I guess that's kind of part of the continuity proof. So let me get back to that in a second. Yeah, yeah. So let me just state the theorem first, and then I can define the terms appearing in it. So this is a theorem which says that the space of quasi-maps, so quasi-map space of quasi-maps modded out by complex gauge transformation, and that is exactly Q map GK X is homeomorphic. So this is more than a bijection. So this is homeomorphic to the space of vortices on those kinds of surfaces. Yes, I want to. What is the vortex analog of quasi-maps? It means that you take a curve in a nodal curve in MGK bar and replace the markings and nodes with the cylindrical ends and put a family of metrics on these curves. And define vortices on those curves. So those objects are the vortex analog of quasi-maps. Okay. So the space of vortices on surfaces with cylindrical ends. Modded out by unitary gauge. So let's call this and yeah, so this space has a, this space is compact. So in both cases, we need to fix if you fix a homology class, they are both compact. So both these spaces are compact, and this has a this is like a Gromov compactification. And in the process of compacting it, you may produce bubbles of this form, like between two, at a nodal point, you may produce a further cylinder. So these kinds of things can happen, but this is a perfectly legitimate candidate for a quasi-map. So anything that Gromov compactness gives you, it is okay with this site. So yeah.
I was kind of curious, emphasizing here that
Yes, we didn't work on the homeomorphism. It's likely to be a homeomorphism. It's a matter of, writing it down. Yeah, I am not very sure about the algebraic side, the topology on the algebraic side. So, but it's very likely to be a homeomorphism. Okay, so I have 5 minutes. And let me talk a little bit about the proof of these, the Hitchin-Kobayashi theorem. Sorry? Yeah, this is for any genus. I guess, no, there has to be, the problem is that there have to be some non-compact ends. So there will be, we can't have k equals 0 because then it will be a compact. K has to be positive. Yeah, there is something, I don't remember now. Yeah, we just want to rule out components with no markings. And anyway, yeah, everything there should be at least 2 markings, right, by our axiom of quasi-map. So, right, so we need at least 2 markings. And yeah, maybe I'm missing something, I should check, yeah. Okay, so let me, how much time do I have? Do I have 10 minutes or 25, 12:25? Okay, let's see how far I get. Outline of proof. Yeah. So okay, I'll just keep this very brief. So the main ingredient is a gradient flow argument. Yeah. Okay. So we consider the gradient flow of the functional, which is the L2 norm of the vortex functional. And why do we do this? So let's just go back to the finite dimensional case. So this is really the norm square of the moment map. So the gradient flow of the norm square of the moment map on X. The first thing is that it preserves GC orbits, because the gradient vector field of this guy by a very simple computation is J of phi X applied to X. So this is tangent vector at X. And so the gradient flow, if you flow along this, you would stay in the same GC orbit and you reduce the value of the moment map, which is what we want to do. So that's the perfect thing to try and do. And so the result is that this is my PhD thesis, is that if in case sigma is compact, the gradient flow exists for all time. So the gradient flow exists for all time. So what do I mean by this is the gradient flow is I crossed the line. Okay. DAT star. Anyway, I guess the exact expression is not important, but what I just want to convey is that this is a non-linear heat equation, and the main content of this theorem is that when you do the flow, you don't have any singularities at finite time. You get to go all the way to infinity. And once you have that, once you have this flow, you can look at what does the flow converge to. And let me just come back here because I don't want to be so far away. I just want to finish that theorem. And the flow exists for all time and converges to a limit gauged holomorphic map plus sphere bubbles. So these are fiber sphere bubbles in X. And in nice cases, like suppose in the quasi-map case, it's assumed that X is affine, then it's aspherical. So those can automatically be ruled out. But we don't, for our results, we don't need that. Our results work in the full generality, even if there are spheres in X. So the limit looks like this. And let me continue here. And A infinity U infinity is a critical point of the vortex functional. which means that it satisfies these two equations. Something like this. Yeah, I mean, these are just the obvious equations if you parse it out. And what the second equation so basically what this says is that I'll just speak in words from here. So what happens is that the flow either converges to the zero of the vortex functional, or it converges to something in the middle, and in which case the image of U lies in some set with a non-trivial with an infinite stabilizer, basically. So outside the semi-stable locus. And so some set with an infinite stabilizer means that some set which is far away from our zero level set. And what that helps us in doing is that in this case, if you're not at the zero level set, then there is then the value of the vortex functional has a certain lower bound, which means that if your starting point is low enough, you don't hit any of the bad points, you go straight away to zero. And then finally, the final kind of argument in the paper with Chris is that if given a gauge holomorphic map on C, since our volume is large enough, we can always ensure that our starting point, so we kind of close it up at infinity and say that this value is large enough and we can go to a vortex. And so basically we apply this theorem, which is essentially for compact Riemann surfaces on versions of P1 where the larger and larger subsets have a Euclidean metric, and then we take a limit to obtain an affine vortex. So that's kind of how the proof goes. Maybe I'll stop here.
Trying to understand them. In the statement of the theorem on the left, you have
on the left,
the right behind you.
Yeah, the quasi-maps theorem. Yeah.
So just quasi-maps with k markings and nodes. And on the right, you replace those k markings and nodes by cylindrical ends.
Yes. So the difference between this and this is that this satisfies the vortex equation, and we are modding it out with the unitary gauge transformations. Whereas here there is no vortex equation, and we are modding out with a much larger group of the complex gauge transformations.
And can I intuitively understand why you need to add this cylindrical ends?
Oh, the idea is that if we have a cylindrical end, that ensures that as you approach the end, as you go towards infinity on the cylindrical end, phi u will have to be 0, because there is a, if you want to look at it fully analytically, there is a certain integral involving phi u which converges, which means that as you go towards the end, phi u has to vanish. And phi u is the, phi u vanishing means that you are in the semi-stable locus. Because recall from the Kirwan condition that so if you are in the zero level set of the moment map, you're very firmly in the semi-stable locus. So by making the area infinite, you make sure that you go towards the zero level set of the moment map at the ends. And therefore, on the markings and nodes, you lie in the semi-stable locus and not on the base points.
Any more questions?
Can I ask a question?
Oh, okay.
Hi, Sushmita. So are you fixing the form of the connection on the cylindrical ends, or at least asymptotically? Is the connection itself, is it asymptotic to a certain model?
You mean on the vortex side or the gauge side, the gauge holomorphic map side?
On the gauge, on the vortex side, sorry.
So on the vortex side, I don't, but we always remain in this realm where this there is a certain quantity called the energy, which is, you may have seen this before, which is the sum of the L2 norms of these guys.
I see. So the connection is forced to be flat asymptotically.
Exactly. So this is integrated over sigma. So we always satisfy this condition when we are doing the analysis. So even when you start out with the a gauged holomorphic maps, which is very strange, at infinity you can do a little complex transformation, gauge transformation close to infinity, so that you're in the finite energy realm, and then it has the nice asymptotic properties that you need.
Thanks.
So if the flow always stay in the same class as we started with, or
the same GC class, the script GC class. Yes, that's what that's why I wrote this. So this is a analog of the finite dimensional statement where the gradient flow stays within GC, because this is what the gradient vector looks like, which is an elementary computation.
So what if we start from the boundary of like exactly in the closer?
Sorry. Yeah.
I was just, so can you maybe make the more precise? This depends on the volume form on the surface, because in this relation to
where you mean?
Yeah, there exactly.
Here?
Yeah, right.
Yeah. So the volume.
Quasi-maps you don't fix, right? You don't fix the complex
right.
structure.
So in order to define the space, I need to define a fiber-wise volume form on this family. And this volume form is defined so that in the neighborhoods of nodes and markings, we have a cylindrical metric. So we can fix a family of these metrics. And it's enough to do these, because when you compactify, you may get some additional unstable components which don't appear there, but that's fine because they are just pure cylinders which get the same metric as these ends. And once you fix that metric, then the real definition of an object here is take a C, which is one of the fibers, and define a vortex with the volume form given by this fixed family.
Yeah, one more. What fails in the theorem, if anything, when there are no markings?
Yeah, it will fail, because then our surface will be compact, and then we'll be in this Ignacie's setting. This is only for non-compact. We need a non-compact end for this theorem to work. Yeah.
Any more questions? Okay, let's thank the speaker again.